Let's consider now weak acids and acid ionization constant. A weak acid dissociates in water into the hydronium ion and its anion. We can simply write this as HA in equilibrium with H plus and A minus, understanding that this is in aqueous solution. The acid ionization constant, Ka, is defined as the concentration of the hydrogen ion times the concentration of the anion divided by the concentration of the weak acid. Ka is called the acid ionization constant, and as it increases, the weak acid strength increases. Here are some weak acids and their corresponding Kas. Let's do a problem. What's the pH of 0.5 molar HF at 25 degrees? Here is the equilibrium, HF in equilibrium with H plus and F minus. The Ka is defined as concentration of H plus times F minus over HF, and the Ka is given as 7.1 times 10 to the negative 4. We can write the ice table. We start out with 0.5 HF, 0 and 0 of the ions. Minus X of HF dissociates, and plus X of H plus will form, and plus X of F minus will form. At equilibrium, we'll have 0.5 minus X, X and X. Substituting it into the expression, Ka equals X squared over 0.5 minus X, and that's going to be equal to 7.1 times 10 to the minus 4. Normally we would have to solve this using the quadratic equation, but we can make an approximation here. Since the Kas are very small, then 0.5 minus X is roughly 0.5. If we do that, we simplify the calculation. Solve for X squared, take the square root, and you get 0.019. The hydrogen ion concentration equals the fluoride ion concentration, and that's 0.019 molar. HF is 0.5 minus X, or 0.48. Notice it's not much different. The pH is minus the log of the hydrogen ion concentration. That would be minus the log of 0.019, which evaluates to 1.72. When can we do this approximation? That is, neglect the X in the denominator. A rule of thumb is to take the molarity, divide it by the Ka, and if it's greater than or equal to 100, the approximation is valid. The percent ionization is defined as the ionization acid concentration at equilibrium divided by the initial concentration of the acid times 100%. For a monoprotic acid, the percent ionization is the concentration of the hydrogen ion divided by the initial concentration of the weak acid times 100%. Notice the difference in ionization, percent ionization of a strong acid versus a weak acid. Weak bases and base ionization constants. These are treated pretty much the same. Here we have an equilibrium between ammonia, water, ammonium ion, and hydroxide ion. Kb is defined as the concentration of the ammonium ion times the concentration of the hydroxide ion divided by the concentration of ammonia. Notice that water is not included in the expression. Kb is the base ionization constant, and as it increases, so does the weak base strength. Again, you solve these weak base problems like weak acids, except you solve for OH minus instead of H plus. Here are Kb's for some common weak bases. Caffeine, one of my favorites, is 5.3 times 10 to the minus 14th. It's a very weak base. Ionization constant and conjugate acid-base pairs. If we take the Ka for a weak acid and compare that to Kb for a weak base, A minus plus water, if we add the two reactions together, we get the auto-ionization of water. Therefore, Kw equals Ka times Kb. If you know Ka, you can calculate Kb, or if you want to know Kb, you have to know Ka. Either way, you can get one or the other of the ionization constants.